tried hard, but where did we so long? I hope we could, but I won't start over again. Midday street, moral science, talent disperse in the air. Nobody stopped to sit and wait. Your right seems so innocent. Everything made sense to you. They didn't do me. Did a compromise for the love. Build up in your words. Way of life, way of life. I heard you say we were on the same street. Way of life, way of my Midday street, moral science, talent disperse in the air. Nobody stopped to sit and wait. Your right seems so innocent. Everything made sense to you. They didn't do me. Did a compromise for the love. Build up in your words. Way of life, way of life. I heard you say we were on the same street. Way of life, way of my
Hi, everybody. Welcome back to Chem 140. We are in week 2. This is Tuesday's lecture. And where we left off on Monday, I was going to go over these answers, but we sort of ran out of time. So we're going to do that now. I do need to organize a bit on my screen. I'm moving stuff around on my desk. I'm just basically trying something new every day here. So let's get this up here. So we'll do 2 at a time. We'll just put these 2 on the screen. And then, oh, I got it. Oops, where'd my cursor go? Let's see here. Because I don't think I saved this last time. Yeah, it's still 4,000 by 4,000. So, save. Oops, why won't you let me save? There we go. It hadn't done the action yet. Oh. Oh, Photoshop, why do you have to be backwards from everything else? There we go. Okay. So, Okay, cool. All right, so for this first problem, what we're going to do is we're going to type this just right in the calculator. 0.0019 times 21.39. I really got to look into why Photoshop is being stupid. Didn't do this in Windows 7. So we're going to punch this in. So 0.0019 times 21.39. And what does my calculator spit out? It spits out this number. 0.040641. Now, obviously, we can't keep all those digits because that's way too many Sig Figs. I just realized I can't see the chat, so I got to get that back. There we go. So let's consider the number of Sig Figs that each of these have because we're doing multiplication. Remember that multiplication cares about number. Really, Photoshop? Oh my goodness. number of sig figs in each value that is used. So this number right here has 2 sig figs. And this number right here has 4 sig figs. So of those 2 options, which one is fewer, 2 or 4? Well, 2 is, so our answer can only have 2 sig figs. So I need to chop my answer down to 2 sig figs. Now remember, these zeros are placeholders, so we can't just keep 0.0. That's not going to be a precise answer. But keeping these first 2 would be, and so I would round this to 0.041. All right, so there's our answer for the first question. What about the second one? So I got 8.321 minus, or divided by 4.1. And we're doing division. Division follows the same rules as multiplication. So this is 4 sig figs. And this is 2 sig figs. So our answer should have 2 sig figs. Well, let's punch it in the calculator and see what we get. 8.321 over 4.1. And I get 2.029512.195. Obviously, that's way too many sig figs, so I only get to keep 2 according to our determination right there, because this was the fewer number of sig figs. So I'm going to keep the first 2. And there's our result. So that's the first 2 problems. Let me know if you have any questions about those. Where is my cursor? There it is. Oops. There we go. So for the third problem, we're going to do addition. So we got 3,000, we've got 20.3, and we've got 0.009. Oh my goodness. This is almost unusable, but I can't just cancel the class to try and figure it out. So remember that addition and subtraction care about decimal places, and we're going to work from the right to the left. So we'll look at this position. Is there a sig fig in every spot there? Well, no. These are blanks, right? So we can't use that. Same thing here. Blank, blank. Same thing here. There's a blank here. Now, when you get to the ones place, you might think, oh, well, there's a 0 here for 3,000, so we can do that. But it turns out that these zeros are placeholders. They're not sig figs, so we can't use any of these either. So we have to go all the way to the thousands place before we can actually start reporting our answer. Because the thousands place is the only spot that has a sig fig in every position. Now, for our purposes, remember, we're treating these leading zeros as known. Because they're 0. We know they're 0 for sure. The number is too small. So when I do the addition and I add straight down, this is the result that my calculator would give me. But since I'm rounding to this position, the answer that I would report would just be 3,000. Make sure you don't put a decimal point on that, because if you do, that would imply 3,000 with 4 sig figs and not 1, which is not what the answer is. For this subtraction problem, we'll follow the same rules, but this time when we look at places, The first one, everything works out. It all lines up. So we're going to report to this position anyway. And we'll just subtract like normal. So this problem is not anything really exciting. However, something interesting happens here. If you look at the number of significant figures in your values, so this is 3 sig figs, and this is 3 sig figs, but my answer ends up being only 2 sig figs, and this is the correct answer. Again, addition and subtraction don't care about number of sig figs. So if you applied the multiplication rules on accident here, you'd get a totally wrong answer. Be careful, okay? Make sure you're applying the right rules. This answer we don't even need to modify. It's correct. So be very careful when applying these rules because there are lots of different problems out there that are designed to trip you up if you haven't committed the rules to memory. All right, and then we'll do the last 3 problems. These numbers as written, 6.000 times 2.000. If you count the number of sig figs in each thing, you'll notice, oh, there's 4. So my answer should have 4. So when you report your result, you will get that as the answer. Now, a question that might come up is, well, wait a second, 6 times 2 is 12, and if I was multiplying 6 times 2, isn't that the same as adding 6 twice? So wouldn't I get something that looks like this? How does this work at? Aren't those equivalent expressions? And it turns out that these are not equivalent expressions because what's going on here, this is times 2, an exact number. However, this 2 is inexact. So these 2 operations are not the same. So be careful. There's a lot of bias in these types of operations because you're going to want to treat them how you've always treated them. Yeah, 6 times 2, anyone can do that, right? But be careful because 6.000 is not the same as 6 because it could be 5.9999, which we rounded to 4 sig figs to get 6.000. They're not exactly the same. So be careful. Be mindful of which numbers are exact and which are inexact, because if I had 6.000 times 2 exact, then this would be a valid operation because I'm literally doing this process. But over here, it's not valid. All right, now I got combined operations. So I got a number plus a number times a number. And so we'll write this down, 4.281. It's inexact because it is a measurement. So if I give you a number and say, hey, this is an exact number, because I counted it, then it's exact. But all of these numbers, we don't assume any of these numbers are counted, because you can't really count to 37.3, right? Same as you can't count to 6.000. You would just write 6 in that instance. So we're going to do this part first. We're going to do the addition first. Because it's in parentheses, right? And so I'm just going to add straight down real quick. Oh, you want to know what this is right here. We'll get to that in just a second. So I have some blanks here in these columns, so I can't use these columns. So I'm going to start my rounding to right there. So this number will become 41.6. So this right here is 41.6. And then when I multiply that by 0.00390 in my calculator, I just noticed that there's an issue in this room that I'm in, and that is that the light is just above my head, and if I have my calculator too low, my big fat head blocks the light, and I can't see the calculator. So typing in these numbers into the calculator, I have the wrong color ink here. I get this number, which I'm only going to keep 3 sig figs for. And so I would report this to 0.162. All right, let's do this last one, and then I'll talk about what's special about this problem up here. All right, so the last one, we've got 52.5000 over 3.6 minus 11. So I'm going to do the division first. So first, this one has 6 sig figs, but this one only has 2 sig figs. So my answer to this part is only going to have 2 sig figs. So let's punch that into the calculator. 52.5000 divided by 3.6, and I get 14.5833333333. Sorry, I paused because I just noticed something. Hold on. If I go like this. Okay, I know what my issue is. For some reason, my entire graphics card is apparently freaking out. Because whenever I draw, the system goes encoding overloaded. And I'm like, how? So I'm going to have to play with that. But at least I have an indication of why this is doing this. So, okay. So, sorry about that. Anyway, we're going to round this number to 2 sig figs, which means that this is going to become 15. So the result of this calculation is 15. And then I'm going to do 15 minus 11. And there you go. That's the answer to that problem. All right, this problem up here. So I think I can actually explain your question. Why is the addition exact? The addition is not exact. The 2 here is exact. And if you are multiplying two things together, so if I have like n times 2, that's the same as n plus itself, right? And since this number goes to the thousands place, if I'm adding it to itself, then I would go to the thousands place. So you get an extra bit of information from doing multiplication with exact numbers because multiplying by an exact number is the same as addition. Now, I can't do this addition if this is not an exact number. So if I multiply by 2.000, that's not the same as exactly 2. And thus I have to use the multiplication rules over here for this problem. So that's the difference there. All right, let me get this back on the screen here. All right, any questions, let me know. I'm not advancing to the next slide. There we go. I'm going to very briefly talk about scientific notation. And then I'm going to talk about something that actually isn't in the lecture slides themselves, but I do want to talk about it in terms of Sig Figs. So for that last problem, if you wrote 4 or 4 dot, they're both one Sig Fig, so you can write either. 4 by itself is probably preferred because you aren't putting in a dot for no reason. Like if you're trying to write 10, for instance, with 2 Sig Figs, then putting a dot there means something, and not putting the dot there means something else. So that would be okay. Now, I am pretty certain that oh, I'm muted. That might also be an issue. Sorry, is it back? OBS is freaking out on me, and I don't know why. Oh my god, this is so frustrating. Okay. I managed to stop it and start it in time. Yeah, you can hear dinging because what's going on is... So if it's blurry, go down to... It should be like right down here. There's a little gear icon. And you can choose HD, and it should fix that. Okay. Sorry about that. That do-do-do-do sound is because OBS is stupid when connecting to YouTube. And it tries to reconnect every second until it actually does so. Like if I do this on Twitch, it does it in one try. But for whatever reason on YouTube, it takes me like between 3 and 20 tries, and that was the most that I had ever seen it go. They did release an update to OBS today, and I just didn't want to update it because if it didn't work and everything broke, then I wouldn't be able to do a class. I'm going to try and update it after class. We're going to see if that works. I apologize that for some reason everything is falling apart. Because of course it is. Alright. So again, if your stream is blurry, there's like a gear icon on your window down below. Oh, maybe not where my arrow is pointing because it'd be below where it says week 2. Hover down there with your cursor and click on the gear and then choose resolution or scaling or something like that and pick HD. Let me see what it actually says. So it says settings and then there's a button that says quality. Click on the quality button and then pick 1080 by 60 and it should get better. All right, we all know how to do scientific notation, right? Like, so if I asked you to turn this number into scientific notation, you'd move the dot to the left and count one spot, for every space you move the dot over, and then you would increase the number for the exponent by that many spaces. Now, depending on the number of sig figs you want to write... Here, so this is actually kind of misleading. So where it says has one decimal place, just ignore this. You could actually have as many decimal places as you wanted to. So for instance, let's say I wanted to have 4 sig figs. I could write 1.000 times 10 to the 13. No problem, I can do that. Maybe I only wanted 1 sig fig. Well, then I just get rid of all my zeros here. So I'd have 1 times 10 to the 13 instead. So with scientific notation, you can have any number of Sig Figs. You're allowed to have as many as you want to when you use scientific notation that will suit the purpose of whatever you need. So if you get an answer in scientific notation, but your answer needs to have 5 Sig Figs, just write a number, a decimal point, and then 4 more numbers, and there's your 5 Sig Figs, and then times 10 to the whatever. Okay? So this right here is part of the answer, but it is not Sig Figs. So you just always include it. But the part on the left, which is your number, that's where you put your Sig Figs. Now, if you have a small number, you just do the opposite process. So this is the diameter of a hair on this person's face. Not face, sorry, head. I guess they're different. And so it's small. Hair is measured in microns. They're micrometers thick. So we're going to move this dot over. Boop, 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 boop. And we're going to just decrease this number for each space that we move to the right. So I move to the right 5 spaces. I'm going to make it 10 to the minus 5. Now, if I wanted more sig figs or fewer sig figs, I could adapt that 8 point whatever. I could do 8.50000, or I could just round to 9, or either one. So that's scientific notation. That's really all we care about for that. And that's how we use it. So there's our summary right there. Now, I do have some exercises for you to do for scientific notation, but I don't really feel like this is a great use of our time. So you can do these on your own. I'm sure that people know how to deal with scientific notation because this is very, very basic math. And then these slides here just talk about how to do math in scientific notation, doing sort of a mental math approach, or just multiplying the numbers and then adding or subtracting exponents. Nobody really does this. Like, this is good for mental math and checking your answer, but as long as you're using your calculator and punching in all the numbers correctly, everything will be fine. So you can use this as a check. When you multiply numbers in scientific notation, you add their exponents, and if you divide, you subtract them. But otherwise, this is not something that you're going to really be tested on explicitly, because you're always going to have a calculator handy. So we're just going to skip straight to the end. And we'll get Unit 3 set up here, so give me a second. That's Unit 2. Oh, there we go. Okay. Just takes a second to load, I guess. Okay, it should be on your screen now. Okay, so we've officially finished Units 1 and 2. And we're going to move on to Unit 3. Unit 3 is actually a pretty meaty unit, despite it only being 3 sections long. And we're going to spend quite a bit of time on this because this is probably the most important skill for the first half of the quarter. And we're going to use this stuff at the back end of the class again. So this is the last of the math, more or less. There's a little bit in Units 4 and 5. And then when we get to Unit 6, we're going to do actual chemistry. Yeah, surprise, this is a chemistry class, believe it or not. All we've done is math so far, but we got to start with something before we can actually analyze chemicals and make measurements for them. So, Unit 3 is all about dimensional analysis. Dimensional analysis is something that you've probably done before, where someone asks you, oh, how tall are you? And you say, oh, I'm 6'0". And they ask, oh, what's that in inches? And you have to do math to figure that out, right? Well, okay, there's 12 inches in a foot, and I'm 6 feet tall, so I'm 72 inches tall. Right? Everybody's done a problem like that. We're going to do problems like that that are more complicated and show a systematic approach for you to get the correct answer every time. Okay, but you have to use this approach. It's called dimensional analysis. And this is the method by which all engineers and scientists and biologists and chemists and physicists do math, is they write out all the units and show how the units cancel out. Now, because many systems exist for measuring things, we're going to be doing a lot of dimensional analysis, and I'm going to introduce you to some systems here. So the first set of the first set of rules that we're going to talk about is the imperial units. Imperial units are stupid, and my understanding is they are trying to bring them back to Great Britain. Why would you do this? So you've probably seen these numbers before. In fact, very recently there was a meme. And for some reason, my caps lock. Let me see if I can find this stupid meme. And then I'll put it on the screen here. Yeah, here you go. So let me capture this on the screen here. You might have seen this meme here. That's way too big. Hold on. And then we don't really need the right side of Imgur here, or even the left side, really. All right. So the countries in red are the countries that use the Imperial System. And this is the setup for the Imperial System. No, Alaska is part of the United States. Why it's listed as... You're right, I didn't even notice that. I just saw it listed in red, and I was like, oh, that's part of the United States. They didn't list Hawaii. Yeah. Anyway, this is the meme. You may have seen this picture before. And this is volume. Here are all the different volumes in the empirical system. Gallon, pint, quart, cup, teaspoon, tablespoon, fractions of cups. 6 teaspoons is the equivalent of an eighth of a cup. 4 quarts, or there are 4 cups in a quart. Like, this is stupid. This is so dumb, right? In fact, there's another one that I have for length that I show students. Yeah, it's this one right here. I actually showed this to a friend of mine who does streaming for a living, and the running joke is that now everything we talk about is measured in fucking barley corns. Let me make this a little wider so you can see it here. But, like, this is so stupid. This is all length. In fact, you can't really see it all because it's just too tall for the screen here. This is length! What the hell? Like, who decided that there would be 96 L's in a skein, but 120 of those is a spindle? Or that 11 fathoms is a Gunter's chain? Like, and like, you've seen some of these, like, you've seen inch, foot, yard, and mile, right? But 1,760? No. Why? Why would you do this? Why are there 3 barley corn in an inch, but there's 4 poppy seed in a barley corn? And a line and a poppy seed are the same goddamn thing. Why? Why? It's stupid. It's dumb. I hate it. Thanks, I hate it. That's the meme we should be using here. right? These numbers are stupid, and the people that made them up should feel stupid. So we're not going to deal with this shit in the laboratory. You're never going to be measuring things in inches because it's a foolish unit. We're instead going to use the metric system. And the reason that the metric system is so useful is because everything is measured in powers of 10. So if I want to look at a millimeter, it's just 10 to the minus 3 meters. If I want to look at a kilometer, it's 10 to the positive 3 meters. Everything is a power of 10. But what this requires you to do, and this is where people resist the metric system, is you get to start dealing with negative exponents. And people don't like to think of 10 to the minus 3, even though it's easy. You could just think of, oh, it's small. There are, in one of these small things, there's a small number of big things. That's what 1 millimeter times 10 to the minus 3 meters reads to me. Oh, in one of these big things, there's a big number of small things. In fact, I'll even go over this. In one of these big things, there's a big number of small things. That's how I think of these numbers. This is a small number. This is also a small number. Now, the reason that we've written them this way is because we want to have an equality, right? This right here, this word kilo, means this number. This word milli right here means this number, 10 to the minus 3. And this word centi equals 10 to the minus 2. So we have something small on both sides. They're equivalent. Here we have something large on both sides. They're equivalent. And so on. Okay. Now, you might not know all of the metric prefixes and all of their values yet. And that's fine. I'm going to show that to you on the next slide. But this is how you should get into the thought process of working with metric. And if you grew up in a country that wasn't the United States, then you're way ahead of the game because you've already dealt with all this, right? You can visualize what a liter is, but it's actually very hard for Americans to visualize what a liter is. And even me saying, oh, it's a quarter of a gallon, that only helps you so much, right? We can visualize what 2 liters is because we have 2-liter soda bottles all the time. But 1 liter is kind of weird. You look at a liter and you're like, oh, that seems really small. But it's a unit of measure that we use. We're just used to dealing with 2-liter bottles and gallons, so. But try and acclimate yourself to the metric system because it will make dealing with stuff in the sciences way better. All right. Now, any conversion between imperial and metric. So if I wanted to know how many feet were in a meter, look it up on Google. Don't commit it to memory because those conversions use weird decimal numbers that are not worth memorizing. But for anything metric to metric, I am going to ask you to commit it to memory just so it makes your life easier. If you're always looking up how many nanometers there are in a meter, you're going to waste a lot of time on quizzes and exams, and it's not going to be fun for anybody, right? Now, again, we have adopted the metric system in the sciences as the standard. That's the S in, well, it's not the S in standard. S is system. But you could think of the S as being standard. We have standardized all calculations to use metric units. And the reason for that is because if I just were to look at lengths, I showed you all the different imperial lengths, but are there other lengths besides imperial? Yeah, it turns out that there are. These are all different units for length. My favorite of these is this one. The smoot is the height of a civil engineering instructor at MIT, and it is used primarily to describe the heights and lengths, I think, of bridges. So a smoot is approximately 6 feet tall. And it's named after, I think the instructor's name was Smoot. It's a joke unit. What are furlongs used in? Horse racing. I don't know what the fuck else they're used for. Like, that's it. These units are all very, very specific, right? I don't even know what a gradus is, or a click, I think a click is like from Star Wars, right? So all of these units are extremely specialized for like a very particular thing, which makes them kind of useless if I were to say like, oh, my apartment building is 7 smoot tall. Like, you don't understand what that is because you're not a civil engineer, right? So we've adopted a specific unit to do all of our calculations in. So anytime we use length in this class, we're going to use meters or some derivative of it. So a click is just a kilometer. Okay. Oh, it's 100 yards. I don't know what it is. Anyway, the point is it's ambiguous as indicated right here. Right here. And also right here. We don't know which one is true. Anyway, we're going to use meters. Now, this system of units is French. This is the good thing that France has given us. The other two good things were baguettes and French fries. And this is called the System International de Units, or just SI units. So whenever you hear SI units, you should think, oh, these are the standardized units that we use for science. Yeah, French fries aren't even French. That's a joke. Like, that is absolutely American. We take everything and dunk it in boiling fat. And then it's delicious, right? Like, I can't fault it. Fried food is great. All right, let's talk about the units that we are going to use in this class in terms of SI units. We're going to look at 5 different dimensions in this class primarily and operate in these dimensions here. Length is the distance between 2 points in space, and we're going to measure length exclusively in meters. Oh, they're from Belgium. I didn't know that. Okay. Whenever I think fried anything, I think, oh, that's probably America's doing, because we just fry everything. I'm trying to think of like things that are fried in other countries, and I can't think of anything. Not like deep fried in oil. How much matter does something have? How much stuff is contained in my can of polar seltzer here? We're going to measure that mass in grams in this class. Now, this is sort of a just technicality. The SI unit of mass is the kilogram. Ooh, that's a good idea. Yeah, tempura and katsu are definitely fried. So I guess we haven't cornered the market on it. Now, the SI unit of mass, the kilogram, the reason that the kilogram is the SI unit and not the gram is only because a kilogram is a more convenient amount to use for more applications. For example, as an engineer, you're not going to be working in grams very much unless you're making a flea circus bridge or something like that. Likewise, if you're a physicist, you don't deal in grams because you're dropping macroscopic objects. Like if you use a bowling ball, you're going to measure it in kilograms. And thus, many units in physics are derived from kilograms. For example, the Newton. The Newton has a kilogram meter per second squared in there. So when you measure force, there's a kilogram component in there. So just be aware of that when you get to other classes. You're going to see the kilogram more than the gram. But for chemistry, we use grams a lot. So that's why it's notated like that here. Time is the time interval between any two events. I realize that's circular definition. I shouldn't have said time. It's just the interval from instance A to instance B. We're going to measure time exclusively in seconds, and there are virtually no other no other units that really matter to us that aren't some derivation of seconds. For example, a minute is a derivation of seconds. There are 60 seconds in a minute. A day is, to some extent, a derivation of seconds. So the second is our definition, and then all the other units we could just convert up or down from seconds, however we need to. Temperature is going to be the amount of thermal energy an object has. You could also say the amount of kinetic energy its molecules have. If you've taken chemistry, you might know about the ideal gas law. We're going to talk about that in more detail in 162? Yeah, 162. We'll talk about the gas law. But for now, temperature is just measured in Kelvin. We're going to use Kelvin instead of Celsius and Fahrenheit. Fahrenheit is stupid, and Celsius has some issues with it that prohibit us from using it in math. We'll talk about that in Chapter 5. And then finally, quantity. How much stuff do you have? How many objects are in this bag? How many atoms are in this baseball? We're going to count those numbers of objects by using this unit. And this is actually a new unit for people who have never taken chemistry before. This is called the mole. The word mole actually does not come from the word molecule. It comes from Latin for, I think the word means pile. So if you have a pile in Latin of stuff, we're going to use the mole. And a mole is a huge number. We're going to introduce this number later. We're going to say a mole of things is Avogadro's number of things. So if I gave you a mole of moles, for example, oh, and there's the conversation topic right there. A mole of moles is so many moles that it would like fill the moon, like completely full. We could have a slightly smaller moon made of moles that would then implode upon its own gravity and like cook. Yeah, XKCD is amazing. I read it daily. You know, when they post one. So those are the 5 units that we're going to use. We're not going to worry about the mole until unit like 11. So you don't have to worry about the mole for now. But the other 4 are going to come up more or less sooner or later. And we'll talk about those fairly shortly for some of these. Now, as we use these units, these all represent a fixed quantity of stuff. So for example, if this is me, then a meter would be about this long. And a kilogram of stuff would be about something this sized, right? Now, what if I wanted to measure an elephant, I guess? There you go. There's my elephant. It doesn't really seem appropriate to measure my elephant in meters if he's really, in centimeters is what I meant to say. If he's tall. So a meter, like he might be like 4 or 5 meters tall. But what about kilograms? Maybe kilograms is too tiny. Maybe he's more like a megagram because he'd be 1,000 kilograms, right? Which would be 1,000,000 grams. Or what if I'm measuring a skyscraper, which goes off the damn page, right? Measuring that in kilograms might not be super useful either. Or what if I'm measuring a helium atom? Then none of these are helpful to me at all, right? You can't measure a helium atom in kilograms. So there are lots of different sized objects in the universe. And having a one-size-fits-all unit doesn't really work because these sizes don't fit all things. So what we're going to do is we're going to modify our unit. This will be our base unit. With a prefix. And whatever I put in front of this unit will then dictate its new size. For example, if I do this, I have a much bigger unit. If I were to do this, though, I now have an extremely tiny unit. So knowing what all of these prefixes are is going to be very crucial for helping us scale a unit. I don't know why I'm waving my hands, but I'm waving them to scale, like big and then small. They're going to help us scale our units to acclimate to whatever purpose we need to use it for. Okay. My mouse is stuck because the mouse cable doesn't go this far from where I put my mouse. There we go. So I'm going to show you those units right here. And I'm going to highlight the ones that I think are worth memorizing. That said, you should probably commit them all to memory. So everything from giga, well, okay, just these three, actually. And then all of these. So the ones that I've highlighted in yellow are the most common. Hecto and deca, not super useful because they don't really come up that often. We tend to use the engineers units, which are in powers of 10 to the 3. However, deci and centi are common enough that we include them. Hecto and deca are not common enough. And so my recommendation is to definitely commit these to memory, or at the very least, like print this slide out and just have it handy. Because you don't want to look this up online every time. How many milliliters are in a liter? Like, you don't want to do that. Now, like I mentioned before, when we're writing our equalities that contain these, the word and the number have the same value. Now, we're going to replace the word with a symbol. I'm not going to write out the word micrometer. I'm going to write mu, which is what this is, and then m. So how do we go about writing conversions for these equalities here? And so if we go over to this screen, I'm going to do this real quick. I'm just going to put that one on the screen. And then I go back to Photoshop and I clear everything. There we go. So if I'm going to write a conversion that represents micro in that number, here's how I do it. So I'm going to throw down the equal symbol first. And I want something from the conversion on both sides of the equality, right? So if I want micro to be 10 to the minus 6, now I can just add meters to both sides. So meter, meter. And there you go. They're equivalent. One of these things is equal to that. Let's do another one for megameters. So if I have... Oops, hold on. My M was not very big. So if I have 10 to the positive 6, now I can just go meter, meter. And so one of these things is 10 to the positive 6 of those things. That's how you make these conversions. You want to have one of each thing on each side of the equals, right? Because that's how you get an equality, right? They have to have the same thing on both sides. If you put the prefix and the number on the same side, it's not equal, right? Then you just have everything on one side of the balance, and the balance will tip. So that's how we can create these conversions. And you can do this for any thing on the prefix table there. So if I want to do nano, so nano is 10 to the minus 9. And then we'll just put in another unit. Now, I've been using meters here, but I could use any of the base units that I want to. So if I want to know how many nanoseconds there are in a second, there you go. 1 nanosecond is 10 to the negative 9 seconds. I can replace this with liters, or mole, or Kelvin, or whatever I wanted to do. That's the power of using metric prefixes. It's just very, very handy with just knowing what the base units are, and then these numbers, we can scale absolutely everything. And that's cool. That's why we like it. When we come back from the break, I'm going to talk very briefly about various units of length. Or not various units of length. I'm sorry, various SI units, just a little bit more detail. We're probably going to skip through these slides for the most part. But we are going to take a break. Is my timer captured? Oh, I got to clear the timer. Here, hold on. That was from yesterday. So I'm going to start the timer. We'll take a 10-minute break. I'm going to get more Persona 3 music going. And then I will return in just a little bit. So I'll see you in a bit.
I've never felt like so miserable. I've never felt like thinking this will last forever. They're just with me. You gotta tell me you can all over me. When stars smile and move, what a hollow in your eyes, just dialing your number, fading to place the last two, praying that how the moon reaches us. If you hold me tight, feeling happy so close, will this last long? I've never felt like so miserable. I've never felt like thinking this will last forever. They're just with me. You gotta tell me you can all over me. When stars smile and move, what a hollow in your eyes, just dialing your number, fading to place the last two, praying that how the moon reaches us. If you hold me tight, feeling happy so close, will this last long? I've never felt like so miserable. I've never felt like thinking this
Hi.
will last forever.
Fears awake, anger breathes loud, face reality, never be charity. The enemy you're fighting covers all society. Damn right, mommy's not here, gonna fight all night. shadow, 10 o'clock direction. Seize the moment, destroy the nation. You rhyme slow motion, give me motivation. Breathe out now, and then on arrival. Round up around, spit out, all over. Rhyme like a rolling stone, come in the crowd. Watch out the moon, that this too loud. This was this sound, and bombs whole ground. So round up, don't ease your pace, cause enemies brutal. Moment of truth, there ain't no truth. You're the only one world, one love. But the battle goes on, shadows all mass destruction.
Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby.
Battlegrounds right here. It's a man's world. Gotta get ready for this right here. Hey, yo. Here's a wake, anger breathes loud, face reality. Never be charity. The enemy you're fighting covers all society. Damn right, mommy's not here, gonna fight all night. Right here, shadow, 10 o'clock direction. Seize the moment, destroy the nation. You rhyme slow motion, give me motivation. Breathe out now, and then on arrival. Round up around, spit out, all over. Rhyme like a rolling stone, come in the crowd. Watch out the moon, that this too loud. This was this sound, and bombs whole ground. So round up, don't ease your pace, cause enemies brutal. Moment of truth, there ain't no truth. You're the only one world, one love. But the battle goes on, shadows all mass destruction.
Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby, down, 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 down. Oh yeah, down, 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 baby, baby, down, 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 down.
Battlegrounds right here. It's a man's world. Gotta get ready for this right here. Hey, yo. Here's a wake, anger breathes loud, face reality. Never be charity. The enemy you're fighting covers all society. Damn right, mommy's not here, gonna fight all night. Right here, shadow, 10 o'clock direction. Seize the moment, destroy the nation. You rhyme slow motion, give me motivation. Breathe out now, and then on arrival.
Sorry about that. I was trying to figure out this Photoshop issue. So I let the timer go a little long there. So let me do that. Boop. So I tried something, and let me see if does this do anything to... Am I overloading the encoder? Yeah, I'm totally overloading it still. I might have to, let me close this real quick. Not the stream. The stream will stay up. It might not initialize that setting until I restart Photoshop. Sorry, give me just a second. Oh, that's what's going on there. I mean, it's a little better. Okay. Yeah, I don't know if I'm going to be able to fix this right now. Okay. Anyway, let's continue. So, on the screen, I have a picture of a meter stick, and you can see marks on there for every centimeter, numbered 1, 2, 3, 4, 5, etc. Right? And those little objects there, those are called stir bars. The stir bars are used in order to... Sorry, I'm still playing with Photoshop. I gotta stop doing this. The stir bars are used in order to just mix stuff. We have magnetic stirrers in the laboratory. And what those do is they allow us to mix a solution without having to contact it with like a rod or pick it up or something like that. It's just convenient. Now, the meter itself, not super useful in the laboratory. We don't really work with meter-sized objects because a meter tends to be too big. So we're going to be working with centimeters and millimeters very often in the laboratory when we just hand you objects, you know, when we actually can go in the laboratory. But when we look at molecular objects, we're going to be looking at distances that are much, 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 much smaller. So the micrometer is still too big. The nanometer is used for light, and the picometer is used for interatomic distance. So we'll be using those units later on. This is a balance. Balances just tell you the mass of stuff in grams. Kilograms are too big for us. So we're going to more or less stick to grams. However, we might also be using milligrams, depending on the application. Now, we're going to mention this a little bit later when we talk about mass versus weight and then force. When we get to Unit 4, we talk about matter. Sorry, not Unit 4, Unit 6. We're going to talk about how gravity is mass times gravity. I'm sorry, not gravity. Sorry, weight is mass times gravity, and mass is part of that. An object's mass is just what it is. It's constant. But an object's weight is dependent on where it is in the universe. So if you're standing on Earth, your weight will be different than your weight on the moon, for example. We'll talk about that again in a little bit. I don't really care about these slides except for this right here. Volume is just the space that something takes up. And it's called a derived unit because we derive it from one-dimensional units. So I'm taking 3 lengths here and multiplying them together to get a volume. And really, all we care about for volume is the liter. And if we define the liter as just a 10 centimeter cube, 10 cubed is 1,000, so a liter is the same as 1,000 cubic centimeters. And if we divide both sides by 1,000, then we get this equation right here. A milliliter and a cubic centimeter are the same thing. And that's particularly helpful. Keep this one in your back pocket, because this will save you a lot of obnoxious unit conversion if you remember that this is true. Oh, I have cubic centimeters, and that's the same as milliliters. So you can get from a cubic unit into a liter unit very easily if you go through this conversion. So that one I just think is worth keeping handy. All right, now that we've seen all the units, let's actually do some calculations with them. And we're going to be doing quite a few calculations here. We're going to start doing some today, and then we're going to basically all day on Monday next week, we're going to do more dimensional analysis. All right. Now, if we go back to those metric tables that I showed you, the big one that I highlighted yellow and said, try and memorize these, it's worth it, or at the very least print it out. It's an online class, you can have it with you. Using those tables, we can write out definitions that they're just true, they're definitions, right? So if I wrote this is true, because here's my centi, and here's my 10 to the minus 2, and I go meter, meter, and I'm done. And I could do that with all of these things. Oops. Now, what we're going to do is we're going to use these in a special way. And in order to do that, I first have to, and I don't know if this will appear yet. Hold on. There we go. Okay. What I first have to do is do a little bit of algebra here. So we're going to take the top equation there. 1 centimeter equals 10 to the minus 2 meters. So 1 centimeter equals 10 to the minus 2 meters. And what I'm going to do is I'm going to divide both sides by the same thing. This is actually a lot better. I told it to use my CPU instead of my graphics card because the graphics card being used for OBS, and it seems to be working. Okay, so now that I've done this, you might think, well, what's the point of doing that? Well, here's what happens. What happens when I divide something by itself? And this could be anything. I could divide 7 divided by 7, orange divided by orange. What happens? What's the result? Yeah, they cancel, right? So if I get rid of them, they go away. Dividing something by itself gives you 1, right? Now, it's very important to say that it doesn't just disappear. Okay, it doesn't become 0, it becomes 1. Anything divided by itself is 1. So this side equals 1. Now, the other side doesn't cancel out at all. In fact, the other side just stays how it is. Okay, well, that's interesting and all. All right, we're going to write this again. I don't know what happened there. And now this time I'm going to divide by the other side. Oops, hold on. Sorry, I messed up. We're going to divide by the other side, which is in meters. There you go. So now I could do the same thing here. Meters and meters cancel out. And 10 to the minus 2 and 10 to the minus 2 also cancels out. Everything cancels out on this side, so it's now just 1. Now, I have two expressions here. On the left side, I have something that equals 1. And on the right side, I have something that equals 1. That should be me underlining it. Therefore, what must be true about these two things? Well, if something equals 1 and something else equals 1, those two somethings must equal each other, right? So we've demonstrated that these statements are equivalent. And that's helpful for us because we can apply these to dimensional analysis. And I can use whichever form I want to. That being said, only one form will help us convert units from one unit to another. For example, let's suppose that I had a distance of like me walking to the grocery store. And I knew how many meters it was. And I wanted to figure out how many centimeters that would end up being. So let's suppose that it's 1,800 meters to get to the grocery store. And I want to know how many centimeters that is. How do I figure that out? Well, what I could do is I could multiply these, the number that I'm starting with by one of these terms. And if I can do that and the units cancel out, leaving only the units that I want, I will know the answer to the problem. So I'm going to look at the unit on the left first, and I'm going to write it down. And I'm going to notice that my meter does not cancel out with a centimeter because the meters are not on the opposite. So what I end up getting when I do this is I get something like this. What the hell is this supposed to be? Nobody knows, because this is not correct. The units did not cancel out. So if you chose the wrong conversion factor, you get a Garbo answer. And you'll know that it's Garbo because the units didn't cancel out. What is a meter squared per centimeter? I don't know, right? So if that happens, you got to flip it over and use the other conversion. When I do this now, I have something times something divided by something. So these cancel out. And you'll notice that only this unit is left over, which is what we're trying to solve for, right? So if I do this math, 1,800 times 1 divided by 10 to the minus 2, I will get the correct answer. And when I punch it in the calculator, I get that. And that makes sense, right? Because centimeters are smaller. There should be lots of little units in less bigger units. So we have used these conversions, one of those at least, to figure out how many centimeters are in this number of meters. This is called dimensional analysis. First, you're going to take some quantity that I ask you about. You're then going to have to choose a correct unit to convert to, and then apply dimensional analysis by setting it up so that the units that you don't want cancel out, leaving only the units that you do. Okay, that's the theory behind dimensional analysis. And in practice, this is easy to do, but it can take some effort to master. And so our objective here for 140 is to give you so many of these problems that by the time they're coming out of your ears, you're like, okay, I know how to do it. I hate it, but I can do it. And then there we go. We've taught you something, right? So you're going to be so sick of the problems that I give you. You're going to get so many problems about orcs riding motorcycles down highways and finding buried treasure and measuring their weight in money and random crap like that that I'm just going to make up because I want you to do dimensional analysis over and over and over. And that's the point. Because what we're going to eventually do is we're going to start doing dimensional analysis with chemistry units. We're going to say, okay, how many grams are there in a mole of hydrogen? Okay, how many moles are there in a liter? And so on and so forth. And you're going to have all these crazy units that you're going to string together. And it's not going to make really much conceptual sense at all what you are doing, but because you know how to do dimensional analysis, you can trust that you're doing it correctly. So we're going to start you with familiar stuff. Like, I drive to work 20 miles. How many centimeters is that? You can do that now. This slide is just showing the same sort of process that I just did to get these conversion factors. If you are just setting up the conversion factors, you don't have to do this process every time. Like, I'm just showing that, hey, this is true. What you can do instead is you can just take this equality and put one thing on the top and one thing on the bottom. And you can then flip it however you want to. Now, this is just a helpful hint on how to arrange things. But really, remember, you want to put the number and the prefix opposite the bar. Because it's got to be equal, right? It's got to equal 1. They have to balance out. If you put 10 to the 3 minus 3 and then you put the lowercase m for milli together, you get the wrong conversion. Okay. So again, make sure that you have the correct orientation of where the prefix and the number go relative to each other. But once you've got all that down, you can then use this to do any conversion that you want to. Now, for other conversions, such as Imperial to Metric, these are just online. For example, if I go to Google, let me get Google up here. And I say metric to Imperial. Oops, let me just do inches to feet. Oh, there we go. That's what I want. So let me capture this. That's not at all what I want. That's just blank. So if you type in something like this on Google, then you can find all of the different conversions here, or a whole bunch of different units. You can't actually see the pull-down menu, unfortunately. So I can do volume, and I can do any units that I want to here. Alternatively, you can do all of this on Wolfram Alpha, and you can get the conversion that you want to. Now, can you enter any number that you want to in here? Well, yeah, you can do that too, and Google will calculate it for you. I'm going to specifically suggest that you don't do that for practice purposes, because when I test you on these questions, I'm going to know that this is an option. And if I say, oh, find how many feet there are in 792 kilometers, and if you just go, oh, okay, well, there's the answer. I mean, yeah, I know you can do that, right? But what I'm going to do is I'm going to make up a unit, and I'm going to say, how many, like, squips are in a kilometer if a squip is 17.5 inches? You can't do that on Google, because Google doesn't know what a squip is, right? So you're going to have to use these fictional units with conversions that I give you. And if you haven't done the process, you won't know how to do it. So for now, strongly recommend that you don't just type it into Google to get the answer, and do the dimensional analysis. Later on, once you have mastered this, you just look up the numbers all you want to, because I won't care at that point. We're going to be focused on other things in the meantime. So for now, use the conversions where you have one of something and then figure out whatever the rest is. So if you typed in meters to inches on Google, it would tell you 1 meter is 39.37 inches, and so on. Now you could do the same process. So if I am, I gotta do the math here, 72 inches tall, and I want to figure out how many meters tall I was, I could use this conversion down here. But I need to set up the units so that they cancel out. So this unit right here and this unit right here have to match. So my inches needs to go on the bottom so that they'll cancel out. And then I'll just put the other unit in there, and then I'll fill in the numbers, right? So how tall am I in meters? 72 over 39.37 says 1.83. And there you go. So this is how we're going to be doing basic dimensional analysis. Now, the last thing we got to do with any problem that we're going to be doing for dimensional analysis is you got to check Sig Figs, right? So if the number I gave you had 3 Sig Figs at the start, and these numbers have 4, how many should my answer have? Well, this is the fewer, so it should have 3. So we're putting everything we've learned together. Very important that you don't just think, oh, Sig Figs are a curiosity. That's cool that that exists, and then never use them, right? So we're going to use everything together all the way up until the end of math here. Now, you could do this for any dimensions that you have or want to calculate. If you don't know what the conversion is, look it up on Google. Now, oops, I didn't have the pen selected. Whenever you have a metric to imperial conversion, something in there will almost always be an approximation. There is one specific one that is not. Inches to centimeters is a definition, which is weird. We're going to just operate on the assumption. Oh, excuse me, I had to stretch. We're going to operate on the assumption that these are all approximations. So what that means is that in exactly 1 meter, there are approximately 39.37 inches. So if you just wrote this like this, in 1 meter, there are 39.37 inches. The number that isn't the 1 is approximate. So this one is approximate. And this one is approximate. And so what that means is that whenever we use metric to imperial conversions, we're going to have to use Sig Figs based on the conversion. But what about metric to metric stuff that we were working with before? Those are all counted. There are 1,000 meters in a kilometer. We've just defined it as such. We've counted them up. And therefore, those are all exact conversions. Okay, so remember that when you're trying to consider Sig Figs, and I will remind you of that countless times this quarter as we do our dimensional analysis practice. So we've already talked about how things cancel out. Now, later on, we are going to be doing a bunch of units at a time, and we can cancel out all of the units that appear on the top or the bottom of the equation. So if I multiply all these things together, these would be the units that were left over. But if I have something like this, everything that matches cancels out. So you can do all your multiplication at once. What we're going to be doing is I'm going to just be like putting a giant train track type thing of all of our units, just one after the other after the other. And then we're going to just cancel everything out that can be canceled out. and whatever is left will be our answer. Okay? So if we can cancel out the units that we don't want and leave only the units that we do, we can solve any problem. So let's do another example here. So we'll go back to the Photoshop window here. I got to clear all this. I didn't actually catch the problem on there. There we go. There we go. Okay. So we're going to use dimensional analysis to convert 1.52 meters into inches. So first thing that we got to do is we need to find a conversion between meters and inches. And according to Google, 1 meter is 39.37 inches. Not just inches. There we go. And so we need to use that conversion in this problem somehow. So I need to put one of these units in this position down here so that it cancels with this meter. Which one will I put? Well, we got to make a match, right? So they cancel. And the other unit goes on the other side. And then we just fill in the numbers. 1 meter, 39.37 inches. So let's type out all that in our calculator. And the number that my calculator spits out, we'll write down the whole thing this time. 59.8424. And then we also have to write out the units that were left over. And there you go. There's your answer. We just now need to do the last step, which is, of course, Sig Figs, right? So how many Sig Figs does this number have? 1.52? Has 3 Sig Figs. 39.37 has 4 Sig Figs. That one is exact. In exactly a meter, there are approximately this many inches. So my answer should have the smallest number of Sig Figs. And that's that. And that's the answer I would report. So if I was measuring an object that was height 1.52 meters, and I wanted to know how many inches that would be, it'd be 59.8 inches. All right. Oops, I got to click over here. Oh my goodness, this mouse. I will figure out a setup by the end of the quarter. All right, so now that you've seen this process, what I want you to do is try this one. So this slide is sadly obsolete. I moved and I had to get rid of my motorcycle, so I donated it to Make-A-Wish Foundation, I think. So I once owned a Harley, and it weighed 625 pounds. What would the mass of that Harley be if it was in kilograms instead? Okay, so first things first, you got to find the conversion from kilograms to pounds. If you're at your computer and you can do that, which you are because you're watching this stream, go to Google in a different tab and type in 1 kilogram equals X pounds or whatever, or kilograms to pounds, and just get the basic conversion. So how many kilograms are in a pound, or how many pounds are in a kilogram. And then do the dimensional analysis like I just showed you for practice. Now, of course, you could type in 625 pounds to kilograms in Google. That's not going to help you on the quiz, though. So do this problem, write out the dimensional analysis, and then type in your answer to the correct number of sig figs in the chat. And I'm going to give you about 2 or 3 minutes to pencil it out while I try and untangle this mouse cord. So I'll be right back. All right, 1 more minute. We'll go over the answer. All right, so let me get this over here. All right, so first we got to look up a conversion on Google, and I only have one of these memorized, so I actually have to go get the other one too. So according to Google, one kilogram equals 2.204 pounds. Now, you might have done this conversion in Google, and it gave you this conversion instead. 1 pound equals 0.4536 kg. Those aren't the same at all, are they? Which one should you use? And it turns out, well, they are the same, it turns out. If I were to divide both sides by 2.204, I would get 1 and 0.4536. So these are actually equivalent, and you can use whichever one you want to. It's just a matter of where the 1 is. So for our purposes, I'm going to just use the one on the left here. Wow, that didn't even draw a line. Okay. So I have a motorcycle that weighs 625 pounds, so we'll go like that. I need to put the pounds on the bottom right here so that my unit cancels. There we go. We'll put the other unit on the top. And then I'm going to use these numbers over here. So 1 kilogram, 2.204 pounds. Punch in the calculator. And I get 283.575 kg. And then lastly, we have to do Sig Figs. This number is 3 Sig Figs. This is exact. This number has 4 Sig Figs. This is the smallest one, so my answer should have 3 Sig Figs. So I would round this to 284 kilograms. There you go. So this is dimensional analysis. Looks like everybody got the correct answer. Now you'll notice that some people were off by a little bit. Generally speaking, Canvas will accept your answer if you are very close in the last digit. So if the answer was 283 and you wrote in 284, it would give it to you. Like you'll notice that my answer that I put on the slide is 283, but my calculation showed 284. And that just could be rounding. I could have used a different conversion from the last time I did this, and that's okay. If you're plus or minus 1 or 2 in the last digit, you're fine. All right, so I'm going to give you these conversion problems to do, and then we'll go over them together, and then we'll call it a day. So for the first set of problems, I have an orc, and the orc's mass is 145 kilograms. I want you to tell me how many grams that is, how many milligrams that is, and how many pounds that is. Now, feel free to start at any point in that problem. So once you've got his mass in grams, you could use that number to go to milligrams, or you could start over. Totally up to you. And then same thing on the bottom problem. I commute a distance of 16.1 miles. How many furlongs is that, and how many centimeters is that? And you can work from whichever step helps you feel comfortable. Do note that you may have to convert to something and then convert to something else and then convert to something else to get the answer for some of these problems. So you might not find how many centimeters are in a mile conversion, but you know how many feet are in a mile, and you know how many inches are in a foot, and how many centimeters are in an inch. So you can do those sorts of conversions if you'd like to, and just string them all together. And I'll show you some of those later on. Go ahead and try these problems. I'll give you about 7 or 8 minutes to do it. Start typing your answers into the chat when you have got them, so that I know where about you are, and we'll go over the answers before we call it a day. All right, let's do as many of these as we can before we run out of time for the day. So let me clear this out real quick. We'll go with that. All right, so for this first problem, we want to turn kilograms into grams, and so we know that a kilogram is 1,000, or 10 to the 3 grams. So I start with 145 kilograms, and I set up the unit so that I cancel out kilograms, leaving only grams. And then I put in the numbers, 1 kilogram, 1,000 grams. I'm going to write that as 10 to the 3, just to be consistent here. Then I would get 145 times 10 to the 3, or if I put it in the calculator and turned it into scientific notation, it would look like this. So there's my mass in grams. Now, if I want to get the mass in milligrams, what I can do is I can just take this number and keep going, right? I also know that there are 10 to the minus 3 grams in a milligram, according to our table from earlier on in Unit 3. I'll set up the units so that they cancel out. And then I'll put in the numbers. 1 milligram, 10 to the minus 3 grams. Not minus, but there we go. Hold on. And there you go. So that would be, and we got to put our unit in too. I forgot to do that. There you go. And then what's the weight in pounds? Well, that's easier if we start from kilograms, right? Because we know that that conversion is true based on what we got from Google. So let's set up the dimensional analysis. We're going to get rid of kilograms by putting it down here to cancel it. Put pounds up there. And then we'll run the numbers. 1, 2.204. And I think that this would be like 330 or something like that. 145, 204, 320. 319.58. But since we're only getting to keep 3 Sig Figs, we would write 320 dot pounds. All right, there's all of the calculations for that problem. All right, and then let's do the last few. This is my commute. I think my commute's actually a lot shorter than this now, but what is the distance in centimeters? So, oh, sorry, let's do the furlongs one first. So, I have here that 1 furlong equals 0.125 miles. And if I go 16.1 miles, how many furlongs is that? Okay, well, we'll set up the units so that the ones that we don't want cancel. Now this is when I used to drive to work. Or maybe I walk around 16 miles in my own apartment. Maybe I do laps around the living room. Don't judge. Gotta exercise somehow, right? It's spider season. That's how much distance I run screaming every time I see a spider on the floor. Only sort of true. I have rescued at least 2 spiders and like 8 beetles in the last 2 weeks. Like every day I get something in my apartment. 16.1 divided by 0.125. I get 128.8, which I'm going to round to 129. For Sig Figs. I haven't gotten like huge spiders. I've gotten like medium, I would say. I live on the ground floor. I'm not used to that. I don't think I had any spiders in my last place because I was on the 3rd floor. All right, and then we'll do this distance in centimeters. Now, I'm going to show you how to do multi-step dimensional analysis next week on Monday. But for now, if you went to Google and you were like, hey, Google, and you said, how many centimeters are in a mile? And it goes, oh, 160,934. That's fine. So we'd set up our units like this, and then according to Google, this is how many centimeters are in a mile. And you just times those together. Now, obviously, this is not the recommended way that I would have you do this problem. But for our purposes, since we're out of time, there's the answer I got. 3, 6, yeah. When we come back tomorrow, we're going to deal with problems where you can't just do that with Google and say, oh, how many of this big thing are in the small thing? And show you do it stepwise, because you could do miles to feet, feet to inches, inches to centimeters, and have 3 conversions. But I've already gone over in terms of time for today, so we're going to stop right there. I do want to thank everybody for coming out to the lecture. I apologize for all the technical hiccups lately. I don't know if I'm going to be able to solve the connection issue problem where like it just stops and I might have to have a part 2. That might just be a thing that I now have because of living here in this place with Comcast. So I apologize that that's an issue that's coming up. I'm going to try and work on the Photoshop thing, see if I can get that to work. All this was working for me in Windows 7 last year. I was using a Windows 7 PC. But now I've upgraded to Windows 10. Everything's breaking. Because of course it is, right? So that's the takeaway. If you don't learn anything from today's lecture of all the dimensional analysis and stuff, it is never upgrade your computer ever. Ever.